Welcome to all of you. It's wonderful to have you here for this second in a series of 6 presentations. And we're really interested this year in looking at a conversation between the biblical account of creation and the account that we get from science, and the connectivity between those, where they overlap, but above all, simply what each is trying to achieve for us as human beings, okay? This evening we are pleased to have Dr. Sarah Yost. I gotta turn this down, I've got a little echo here. Testing 1, 2. Still a little echo. No? It's okay? Okay, then I'll not crank it down any further. We're pleased to have Dr. Sarah Yost, who is a member of the CSB and SJU Physics Department, as our speaker. Sarah was born in Vancouver and grew up in Winnipeg, Manitoba. She did her undergraduate degree in physics at the University of Manitoba, and then her doctoral work at Caltech, and finally a postdoc at the University of Michigan for 3 years. She joined the faculty here in 2007. She teaches a full array of courses, the 2 basic courses in astronomy. We don't have a major in astronomy, so the solar system and stars and galaxies, and then physics, modern physics, quantum, topics courses, and I'm sure a boatload of other things, okay? She also has an active research program with undergraduate students, both during the year and in the summer. She's been actively interested in gamma ray bursts, which is a very technical kind of term. It's the fraction of a second to minutes long gamma ray flashes that accompany the death of certain stars. The emission is very irregular in brightness during the event, but in the events after that event, there's a longer-lived, fainter, smoother afterglow shift that can be studied. So lots of fascinating work out there into the outer limits of our galaxy. We are pleased that Sarah took time in the midst of a very busy schedule to be with us for tonight's presentation. The presentation is entitled Following the Evidence, a Scientific Understanding of the Universe's Origin. Please give Sarah a warm Collegeville welcome.
So this is working now? All right, thank you very much for the kind introduction. As noted, we're going to be talking about the universe's origin, which is the subset of astronomy called cosmology. So we're actually not going to end up talking about gamma ray bursts, which are fascinating, but an entirely different 1-hour sort of presentation. We're going to there's no mystery to this. The punchline is that examining the physical world around us gives a lot of evidence that we are in a universe that began from essentially a single point, expanding outwards about 14 billion years ago. I'm going to talk about the scientific approach that led to this conclusion, the particular Big Bang model that we're in right now, and a little bit of commentary about how this fits in personally with supporting an understanding of creation. I should note this is not some general thing that would be common among all scientists. There's a wide range of perspectives there. I am Catholic. I grew up with a church-going family, and as you noted, I grew up in Canada. I'm certain there are plenty of people in Canada who find a significant tension between their religious or faith tradition and what scientists go and put in the newspapers and so on, and say, this is what's going on. But they don't have the cultural prominence in Canada as you hear in terms of debates in the United States. So while it might sound rather simplistic, when I was young, people were talking about science is telling us what's going on, religion and faith are about why this is. Biblical accounts, well, if you don't understand the math and the science behind it, how would they even put into words, 14 billion years worth of cosmic history? So it would be presented differently by them. It made sense to me. And when I discovered, as I was studying more in terms of physics and astronomy, that when you go and look at the development of cosmology, one of the really big figures in the development of the Big Bang Theory was a Catholic priest. Didn't make me blink at all. Made perfect sense that an examination of the evidence of nature would be something that Catholics and Catholic priests would be interested in, and that it wouldn't necessarily be faith-shattering in any way. So with that in mind, let's move on to a little bit about, it's the way to get this go forward. Let me see, trying this thing one more time. Oh, I think I'm gonna point it this way. That's my problem. Or not. No, let's see. Okay, we'll start with this. Okay, something's wrong with this thing. It should be. There's something weird going on here. I'm gonna click this, click this. Okay, it seems to be frozen. It's not good. One moment. Okay, I'm gonna go back to restarting the slideshow on the first slide and try to click through now. Maybe this will make it go forward. There we go, okay. So here's another cartoon picture of our theory of the Big Bang that works for our universe today. And it's not just the Big Bang theory. Big Bang theories are a class of physical models where the universe starts at a point. The successful model that we have today is called the cold dark matter lambda dark energy, or for short, lambda CDM model. So this particular flavor of Big Bang theory had the Big Bang, everything starting from a point, 13.8 billion years ago. It would have gotten large relatively quickly. As it does so, the universe's matter gets spread out, it cools down. Eventually, it becomes cool enough for the first stars. There's further development of galaxies, planets, and so on as the universe continues to expand. And then in the relatively recent cosmic past, we see evidence in the pattern of how far away supernovae of a given brightness are versus how fast they're moving away from us. So that nearby things are faster than they were further away in terms of the expansion. So we are accelerating the expansion. And that's what they call this dark energy, where in the lambda dark energy formulations, it's a property of space itself, which would cause points of space, not particles, but actual space, to try to mutually repel and therefore accelerate any expansion. This would have always been in the mix, but when things were denser earlier on, the gravity of all the material in the universe would have dominated, and only in the recent past would things have tipped over, allowing that accelerated expansion to happen. So this overall pattern here, and that also will include some things I'll talk about later in terms of how much matter there is, how much energy, and so on, is the lambda CDM Big Bang model. Now, how did we get to this point? To get to this point, let's see if I can keep moving this thing forward. There we go. Oh, I've now managed to go way further back. That's, again, I think I'm gonna have to go and click through. This is way further forward. So I'm gonna start over here with the slideshow. I think I might have to click from here, from current slide. Something is not quite working with these. So you have to go back to 1929, where Edwin Hubble published his evidence that galaxies are uniformly expanding around us. So this is a scan of his picture from his paper there. And so over here is velocity, how fast things are moving, versus distance. This is in units of millions of parsecs, where a parsec is a few times light years. So I'm millions of light years here. A bunch of galaxies, and there's a scatter to them, there's an overall trend. Uniform means that double the distance, you've doubled the speed at which things are moving away. And the way that he got that information was you have to estimate how luminous something is, how much light it's outputting, having an idea about galaxies there. And then how dim it looks, it tells you how far away it is, because the further away things are, the dimmer they will be. And then you have to figure out how fast they're moving towards or away from us is based on the exact same principle that gives a changing pitch to the sound of an ambulance siren coming from behind you moving away, or that allows a cop to catch you speeding. Basically, as a source and an observer are either moving apart or coming together, if there's a wave being emitted, as things come together, the rate at which you get peaks of that wave get bunched together. That shortens a wavelength in light that makes things bluer. And that's what they were representing over here. They called velocities less than 0 would have been coming towards us. If things are moving apart, then you end up stretching out the wavelengths, which for light makes things redder. And they were noticing the characteristic patterns in the light from the galaxies, where you would expect to see precisely placed lines for a particular spectrum with a particular material. They had those lines, they were all shifted. And the shifts were typically these red shifts over here showing they're moving further away from us, with only a few locally coming towards us. So this over here, the way to think of it in 3 dimensions is usually given as a loaf of raisin bread expanding. So this is puffing up by a factor of 2. So this little raisin over here is seeing, which was 5 centimeters away, becomes 10 centimeters away. So it moved 5 centimeters. And the 10 centimeters became 20 centimeters. So it moved 10 centimeters, let's say in an hour. 5 centimeters an hour versus 10 centimeters an hour. And getting off of that mesmerizing look over here, again, back to the raisin bread analogy of the expanding universe. Here they're showing a couple over here that are growing by a factor of 3. And it wouldn't just be one particular raisin. You could pick this raisin here. And those distances have puffed up by that factor of 3. So again, the further one would be moving away from the observer faster. So just because galaxies are moving away from us in all directions doesn't tell us that we're the center of the universe. Because the pattern that we're seeing would be the same as any point in the expansion. And we actually don't have any evidence of there being an edge to the universe, so there's no real definition of what the center of the universe would be. The universe is bigger than we can actually detect at this point in the universe's history. It may very well be infinite. So if that's the case, there's really no center to define in any way that we can at this time. But the interesting thing here, well, there's 2 interesting things here. First off, the way this would work for space is not, raisins puffing out on their own in a pre-existing space. This loaf of bread here, this is like space itself expanding. So not that you have matter that's puffing out into an empty jar that we're filling, but rather that, the balloon of space itself is expanding. And with that, if you think of looking backwards, you could clock everything back. So take this time, clock it back till it's 1/3 the size. Clock it back again. Things that are twice as far away are moving twice as fast. So if you think about the amount of time it would take for this nearby one to actually hit this raisin, the same amount of time a farther one would take to hit the raisin. Everything would clock back together at the exact time. That sure sounds like you could move all of space, even an infinite number of points in space, back to one single point, which you'd call the beginning. So here we are back in 1929 with that, and there were some objections. This over here is in 1948 was when they had a lot of the papers discussing this were published. Bondi and Gould had what they call the steady state theory of the expanding universe. So steady state means everything is staying the same. And over here, the summary starts with saying that you could only use physics without ambiguity if you had a homogeneous, same in all directions, and stationary, meaning not changing universe. So they investigate things, and here was a better version. This is the exact same paper, just a bit better formatted for this kind of use here. So I've highlighted this over here. They accepted that astronomical observations show the universe is expanding. They said, all right, if things are going to be staying the same, we're talking here about cosmology. Cosmology doesn't care about individual stars or individual galaxies in the universe. We're talking about smoothing things out, talking about the average amount of material spreading out. If that's the case, they said the average would have to stay the same, although the individual galaxies might be spreading out. And the way that would work, they calculated based on how much expansion was being observed, that if you were creating matter in space as it empties out, it would be at a rate too low to directly observe with any evidence they would have had at that time. So it would be compatible with the lack of observation to that point. There's a cartoon here. The straightforward interpretation of Hubble's observation is galaxies spread apart and they just get more and more spread apart. Space itself has got a lesser and lesser density of matter over time. The steady state theory would have, here's those same galaxies in the universe. As they would spread out, these old galaxies would keep on aging, but the space between them, when it got sufficiently low density, would have little bits of, well, hydrogen gas pop in. Hydrogen gas will pull itself together eventually through its gravity and form new galaxies and stars. So you have interspersed with the old galaxies, which are somewhere around here and there, you have a bunch of new galaxies appearing over time. So that was the theory they had, and when I said there were objections to this sort of thing, this continues with, this is the same paper, Bondi and Gold, talking about the perfect cosmological principle. They were starting from the point of view that you would have to be able to repeat any experiment in physics at any point in time or space and get the same result. So they were basically saying that including outcomes like what's the density of the universe. So they said a system of cosmology has to be concerned with this as a fundamental assumption. So they came up with this making, matter out of space, as space empties out. They didn't have a mechanism for it, but they said that this would have to happen if this was perfect cosmological principle was going to be true. As I understand, this was never a dominant thing among the theorists and the community, but they were hardly the only people, and they were not crackpots with this. They had others who examined this, pardon me, I've now managed to make this go backwards and by pressing the button in the wrong way. I clearly am, this is clearly flummoxed for this level of technology. So Fred Hoyle also discussed this model for the expanding universe. What I found interesting about his, he talked about it being, Dirac was involved, that the possibility was attractive when you considered aesthetic objections to the creation of the universe in the remote past. That would go against scientific inquiry to regard something that you could observe as arising from a cause unknown to science. Now I'm looking at this from the perspective of decades later, when evidence I'm going to discuss in a moment has settled the issue between Big Bang versus steady state of expansion. But my first thought is this is very alien reasoning to me as a scientist. For starters, why would you have to have all experiments always being the same? You could imagine ways in which if you're setting up a tabletop experiment, you change the parameters of the experiment, therefore you might get different results. So why couldn't the rules of the universe or the conditions of the universe develop in such a way to change results? You should then think about, if these results were changing, what would be the consequence? That's the way of thinking about it scientifically from my point of view. And this over here, against the spirit of scientific inquiry, to regard something observable as coming from causes unknown to science, well, first off, what are you observing? You don't ignore it because you can't figure out a scientific cause. You might consider, could there be a scientific cause for creation in the past? And I assure you there are many, many theorists working on this right now. So again, so you look and follow the evidence and don't dismiss the logical possibilities that would have caused that evidence just because you don't like the fact that you cannot yet consider a way that there could be a cause you could examine scientifically. You might not be able to examine the cause scientifically. It's going to be a problem with the universe. You can't make a bunch of universes in the lab and test out what's the average universe out of a million of them. So we only have the one, and it's sometimes been discovered as being like coming on a crime scene and trying to study it forensically. You don't get a second shot at examining our universe, so there are going to be some things where it just simply is, well, of all the possibilities, here's what we have. Was that likely or not is a question, but you might only have that one possibility because you've got the one universe to work with. So, as noted, scientific inquiry, go and test the theory. I've got over here a cartoon of what would happen if you're considering going back in time to a true point. The entire universe worth of matter and energy is cranked back down there. At some point, you would crank back all of the atoms and all of the light would come together, and there'd be too much energy, it'd be too hot to hold the atoms as neutral atoms. You'd ionize the universe. Or looking forward, eventually you'd get cool enough that you'd allow atoms to be not ionized. Before, it's this hot soup where electrons are easily popped off from nuclei or from ions and float around in this charged, thick plasma of gas. So here it's pictured as this is before you get neutral atoms, and here's after you get neutral atoms. And these bits here that are streaming off are representing light that can finally move between the atoms without knocking into a bunch of free electrons. Because you see, light is electromagnetic energy. It interacts really easily with charged particles. If you make a hot soup of a whole bunch of charged particles moving around, and there's something there, a pattern in it, a hotter spot, an organized ball of something that's emitting a particular pattern of light, okay, it emits a pattern of light. And then those photons of light go and encounter an electron or one of the nuclei there, get absorbed, and then re-emitted in other directions. So you've got light scattering around there instead of streaming out like it can when you've got neutral material in most of the universe. It's like trying to look back into, well, a thick, hot plasma like the top layers of our sun over here. That's what this is a picture of. We can't see through it. The universe would be opaque. And if the universe was opaque, you'd expect it to have emitted light from when it was effectively a hot, thick plasma that's like the top layers of the sun, and that light would stream out. And there's actually an awful lot of empty space. There's a reasonable amount of these streaming out photons that would not have gotten absorbed by anything else. It should be out there. It should be out there, and it should be coming from all directions. And another analogy is you'd look up in the sky, and all around there's clouds. You look up through the clear part of the sky, you'd see clouds where it scatters off. Look anywhere else in the universe, looking through the clear parts of the universe, what they call the last scattering, and CMB stands for cosmic microwave background, if you've heard of that. The background light of the universe is from when it became transparent. So, pardon me. So this is the bit about it coming from all directions. It was detected back in the 1960s, I think, in the first place. Later on, this is the Kobe satellite. It was the first one to get a really good all-sky view of it. So here's the cartoon picture of Kobe saying, hey, within a small amount of variation, they saw light that looks what they call thermal radiation, the characteristic pattern of light, the amount of energy at each particular wavelength in the spectrum. That's like an opaque object with a temperature of 3 degrees above absolute zero. Now, remember I said it should have been hot, a hot, thick plasma. But remember, we're expanding the universe. That stretches out photons. Also that redshift of stuff moving away from us. It's redshifted by the expanding universe, and when you stretch with a redshift, you actually get this exact same pattern of a colder source. So that actually matched what people were expecting. And this is a much more recent view of here's the differences from the average, where from the brightest, hottest bits, the coolest bits, the difference is about parts per million. So the entire sky was indeed producing this light. So this was the death knell for considering the steady state theory of expansion to be serious. And it's considered one of the big pillars of the Big Bang theory, along with the expanding universe evidence of the galaxies. There is a third big piece of information, because you've got this, what else would be going on? And here's where we start to get at the different flavors of Big Bang theory. This is another cartoon here, expanding the universe, scaled in such a way that here is now, size of the universe is whatever size it is now. If you make up the universe of different things, here there's toy universe with different amounts of matter, including they call dark matter that basically doesn't interact with light, it just interacts with gravity. They call the dark energy that goes and expands and puffs, repels parts of the universe. They would all, however, agree that you might have different things happening in the future and different details of the past. The early rapid expansion would get so extremely hot and dense as you get down to the size 0, that you not only make the universe opaque, you do eventually break matter down in ways that you're going to have slightly different amounts of time as you to expand with different flavors of universe. So over here, back to that cartoon picture, you've got the first atoms here was where you could allow light to stream out. Here everything was an ionized plasma, and here things are so energetic that you actually can't hold nuclei together. Individual subatomic particles, the protons and neutrons that form the nuclei of atoms, would have so much energy at the early times that even if they tried to hold apart, they get hit by a photon to give them enough energy to split apart. So there would have been a period of time they call the nucleosynthesis era, which, by the way, is about 3 minutes after the Big Bang, where the universe would have cooled down enough. Here's a whole sort of subatomic mess of the entire universe being so energetic. It's cool enough that you can hold nuclei together, and before things expand so far apart, that's unlikely you're going to have things colliding into each other to stick and build up larger building blocks of particles. So the first thing you'd expect if you allow particles as we know it to exist would be protons and neutrons. Proton could actually attach to a neutron. It forms what you call heavy hydrogen or deuterium. That one runs into another neutron, can form double heavy hydrogen over here. And if there's a proton that comes to the party, you get helium-4. Other things could happen. You could try to add another proton to this thing, and then hopefully end up with another neutron to get helium again. You could have two of these things try to, if they happen to find each other, form helium. You could try to add another proton or neutron to helium there. But the most likely things to happen are small things making slightly less small things. So unless you have a lot of time for things to build up, you're going to be left with lightweight nuclei, the lowest, smallest number of particles to put together to form an element. So hydrogen being 1 proton, helium's got 2, and lithium's got 3, and a few of their isotopes there. And not only do we have a universe dominated by light elements, to a very good approximation, we're 3/4 hydrogen, 1/4 helium, all the stuff that we consider normal for the Earth are heavy, or actually very rare heavier elements. But there's the appropriate relative amounts are there for a particular set of Big Bang theories here. So looking as far back in the past through things like the oldest stars that we can see now, as far away as we can see in terms of gas in the early universe and so on, they look for evidence of how much helium was there. And this is D is heavy hydrogen, how much heavy hydrogen. What do we know about helium-3 or lithium and so on? And it gives us information that actually matches one of the patterns of, well, this is an overall density of the universe, and this is the amount of normal matter over here. So this supports not just the Big Bang theory, but it started narrowing it down. It's got narrowed down more and more and more until we got to this lambda CDM, which is the best explanation of the universe that we've got going right now in terms of a physical model. So this here is a bit more detail about this. This dense paragraph over here is attempting to explain, what gets put together in terms of assumptions. Basically, the model is a whole bunch of math using general relativity and the Friedmann-Lemaitre-Robertson-Walker equations, which I'll leave you to guess which one of those is the Catholic priest. Lambda CDM assumes that the universe is composed of all of these things here in this lovely pie chart. Don't get many pie charts in physics, so this is a nice one to be able to pop up. We have dark energy, which again is the stuff which makes the expansion accelerate. And we have regular matter, which they split up here into the heavier elements, neutrinos, stars, and free hydrogen and helium. This other stuff called dark matter, which we only can detect through its gravitational effects. There is evidence for dark matter beyond just making the scale of the universe and the development of the universe make sense with this. They see evidence of extra gravity on scales of galaxies and clusters of galaxies and so on. So we might not quite know exactly what the dark matter is yet, but it's not just here that we've got evidence for it. So it would be a certain amount required to make the overall development of the universe work within this model here. So dark energy has this particular lambda formulation called a cosmological constant. And the standard lambda CDM assumes that space is flat. This is what this cartoon over here is all about. Flat space is the sort of, well, that's probably what you encountered in introductory geometry. Nice flat sheet of paper, you can draw triangles and circles on, it's all the normal stuff that you expect. Normal grid lines, parallel lines remain parallel, and so on. It turns out that matter and energy can bend light and bend space. Going well beyond this sort of thing here, one of the first vindications of Einstein's theory of general relativity was when he was successful at predicting just how much the patterns of the star field behind the eclipsed sun would be distorted by the gravity of the bent space right next to the sun. So material and mass and energy go and bend those straight lines, and then light has to follow those curved paths, basically. And when it comes to looking at the universe as a whole, smear the whole universe out in terms of its density, there's actually one very particular density, which is parameterized as an omega parameter here, that's called omega 1, that would have the entire set of space-time be flat. Remember, we're not concerned about individual stars and galaxies here. On average, everything would flatten. If you have less than that, they have what they call the open curvature. That has sort of what they call a saddle point kind of geometry, and angles do things like sort of spread apart like trumpets. And if you've got more density than what you need for the flat geometry, you have what they call a closed geometry, like on the surface of a globe, and angles sort of come from sort of a bunched out sort of perspective there. So they basically assume they have exactly the amount for this, that sets a little bit the tuning of what we have over here in terms of from the measurements. And everything we are measuring does fit within that, but they just assume that it perfectly fits. This, of course, is not exactly how it goes into the math that they use. These 6 parameters are put in a whole bunch of different ways here, including things like how fast is the universe expanding locally, what amount of matter we have, what amount of normal matter. The details of this go into those equations, but what I want you to notice is the uncertainties on these are not really huge. They're 1 part in 70, 5 parts in 318. Some of them are a little bit more, 1 out of 24. But we're talking about percentage level uncertainties now, as opposed to, well, we think it's kind of somewhere in this general area of parameters, which is what things were like only a few decades ago. So I think that when I clicked past this over here. In 2008, a cosmologist named Peebles, who happened to win the Nobel Prize this year for his work on the lambda CDM theory, gave a talk at University of Minnesota. In a semester where my teaching schedule actually allowed me to get down there for the physics colloquium he was giving. And his talk included talking about the status of cosmological tests. And so I found my notes from that, and my scribbled horrible handwriting here is that includes lambda CDM passes tests more strict than could have been imagined in the 1960s. And he particularly noted the last, what they call 10 orders of magnitude or factors of 10 of expansion. So it had been tested through the overall development since the universe was 1 part in 10 billion of the size it is now. I have seen things in the literature in the last decade since then that are talking about the last 14 or 15 factors of 10. It's talking like something like 1 part in 100 trillion of the size it is now. would be reasonably well tested in terms of the expansion pattern and the development of structure and so on, matching what lambda CDM says is going on in the universe. I've highlighted over here, CMB was that cosmic microwave background, Big Bang nucleosynthesis was that bit about being dominated by light elements, and then I've got a whole bunch of stuff that I scribbled here, and unfortunately, I didn't write down the exact number of cosmological tests he was discussing. He actually was doing this briefly before moving on to other things, and I think it was something in the neighborhood of about 20 tests that he said it had passed. Now, they weren't all really strict tests. This one over here works for many models, not just lambda CDM. This is some of their evidence for the universe being flat. This is evidence from an experiment called Boomerang. Here's what things would be simulated to look like if it was flat, and here's the different distortions you get with the different curvatures, and it sure looked flat. But also there's this other stuff over here, which I had written down a few of them out of the other dozen or so that I've forgotten. I don't know what they are anymore. Come on, I had something. I did try clicking this. One more try. This is not good. Why do I keep on having trouble with this? Oh, and now it's back at the start. So let me try to get to the particular one. Yeah, back at slide 2. All right, so over to here. And now we go back to the slideshow. Okay, so over here, some of these other tests included, well, these fluctuations of the cosmic microwave background. It's not just the average size, but how many large ones, how many small ones. There's some details in the math there they can worry about. But also things like the amount of regular matter found locally and in early universe hydrogen gas density. Basically, some of these were not the strongest tests in the sense that lambda CDM demands a certain amount of regular matter. We haven't found all of it yet, although we're getting closer. But if you'd found more than was expected, that would break the theory. So it was that kind of, not all of them were really strict tests, but had passed at least 20 of these sort of, some stricter, some more minimal sorts of tests there. So with that, I also add that it's a totally different thing than from Peebles' talk, but we also have no evidence that physical laws are changing on us. And there are people who get disturbed by the scales of the universe and ask, is there some way that you could be changing the physics of what's going on, changing the physical laws in a way that would speed things up, and you could hide the universe is actually much younger than it appears to be, or something like that. Well, the trouble with that is that if you're going to change the physical laws, there are things that we observe that are dependent on different physical parameters in different ways. There's not one parameter that speeds everything up. So for instance, changing the speed of light or the overall gravitational strength, or what they call the Planck parameter, which is the size of the teeny tiny stuff. You have to start worrying about what they call quantum physics. All of those things, if you change them, you affect stuff like how do atoms produce different energy levels that get used in spectra. And so astronomers test for this sort of thing by looking as far in the past as possible at lines in the spectra. So it's constraining fundamental constant evolution, changes in the physics, by looking at lines in spectra for changes in the patterns, because different lines are affected by fundamental constants in different ways. So you could tweak one of them and you'd wreck others in different ways. And with that, they found, going back to us 3 billion years, no evidence down to the part per million. -1 plus or minus 1 part per million type changes. There's no evidence for changing fundamental parameters, at least back 3 billion years in this particular one. And they're not the only ones. It's not a cosmology astronomy one, but there's an evidence of past nuclear reactions on the Earth that would tell you that nuclear activity has been very much through the same rules back billions of years on the Earth as well. So in any case, we don't think that we have some grand illusion going here either with this. So that becomes the question, is there anything left but stamp collecting when it comes to cosmology? You've got these, percentage level uncertainties. Can you make things a little bit more narrow? Let's put on an extra few digits here. Well, yes and, well, not, there are other things out there. there's the questions that are not necessarily cosmology, but been broader in physics. What is that dark matter? Lambda CDM says there is this much going on. And Lambda CDM doesn't have to, exactly say what it is, but other areas of physics, we want to know what the heck's going on with this thing to make it fit into the entire, model of what's going on in the universe. So dark matter, there is room in the model of particle physics for particles we have not yet detected, including ones that you would expect to not interact with light. You may have heard the splash a while back about getting evidence of the Higgs boson related to what helps give things mass. There are other slots out there that are hypothesized that may exist, and they actually think that there are some reasonable candidates for the dark matter in the universe there. So maybe the particle physicists will figure this out. Certainly an open question. And if nothing gets found, it is a question of what the heck's going on with this model. And then there's this lambda parameter making space repel itself. What is it? And there's this bit about, if it's a property of space, again, it's not lambda CDM saying that this is what lambda must be, so much as here's how lambda acts, and the rest of physics tries to figure out how lambda is made. If we're talking about property of space, they look at these properties you'd expect for a vacuum. And you're talking about, there's nothing there. Well, when you get into the physics of the teeny tiny, they call it the quantum scale, their size is too small for you to probe in any normal way. And at that level, there are scales of length and energy that you could expect there might be what they call quantum fluctuations of energy on that scale, even when nothing's there. If those quantum scale properties cause lambda, and that's a pretty big if, it would be expected to be 120 factors of 10 larger than the scale of lambda that we're seeing here. So if lambda came from quantum stuff, it's weirdly small. And so again, that is a question out there that kind of goes beyond cosmology to other areas of study in quantum physics and particle physics and so on. But keep in mind, that's 95% of this pie chart is kind of embarrassingly unknown. We have evidence that something's doing this stuff, but we don't have solid evidence of exactly what it is. There's another couple of things. Why is space-time so flat? It might just be what it is, as I noted before. You've only got one universe to work with. But it has been noted that it's a lot easier to make things that are not flat. And it's not easy to make something which is almost but not perfectly flat. You tend to amplify making things less dense than flat, more open, or more curved and closed if it's more dense than flat. And then there's something over here that has been sort of shoved under the rug to this point, and that's that how in the world did the universe we now observe agree to be the same temperature at the era where the universe became transparent, that cosmic microwave background era? That was about 300,000 years after the Big Bang, as far as the lambda CDM model would put. And there'd be another about 14 billion years from that to now. Light could only travel a small distance between time 0 and 300,000 years compared to the amount that we can effectively observe back to the cosmic microwave background. You'd expect something like 10,000 patches on the sky that would not agree very well in temperature. I said there were parts per million agreement. That's not the kind of difference we're talking about here. And it'd only be 10,000 patches, not that little scattered pattern there. So there is what you call an add-on to the lambda CDM theory here. They call inflation. I should add this over here is something that would be happening about 10 to the negative 40th seconds after the Big Bang. We have nothing at this point that we can use to probe that era. So it is theorized with no adequate way to actually test it at this point. And Peebles, when giving his talk about the status of the lambda CDM model, flat out said he was not talking about inflation, that he would not speak as to whether inflation was real or not, because he didn't consider it something that was even in the realm of testability at this point. Still, the idea would be you've got that little bit of the universe that when it can communicate, you can agree on temperature because you get to mix up your energy. So things cooler and hotter, it gets mixed up, you agree on your energy. They call it thermal equilibrium. If you puff that up rapidly, it puffs past the region that we can now observe of light coming to us from all sides. So you'd still be catching up with seeing one patch of the universe that was agreeing on temperature way back when, and it would take much longer in the future of the universe before we would notice, other patches at different temperatures, if something like inflation happened. People have also noticed that could help flatten something that was almost but not perfectly flat. It would make things flatter, which would help with this sort of issue here, although it might be perfectly flat. So again, you've got lambda CDM, there might be inflation, but that's not something that I would say is testable at this point. It is admittedly, though, something you're trying to bury in the back at 10 to the negative 40 seconds after the Big Bang there. So let's see over here. So back to, is there anything more than stamp collecting? So again, my area isn't cosmology. I did take a look. They are reviewing. There are some small scale problems they found. There was a short review from a few years back, and the main points I got from there is there seem to be some smaller issues. They were okay with predicting the number of large or medium or small galaxies, but the very small galaxies, the way that you would expect structure to form with dark matter and regular matter over time, it wasn't quite matching the observation. And there's something about the shape of where dark matter would end up dominating in small galaxies. And as an observation of our Milky Way galaxy, our nearby galaxy M31, having satellite orbits that are kind of all in one, not all in one plane, but a lot of them in one plane as opposed to being a little bit more disorganized, which might have been expected randomly. But it also seemed as though there was a question as to whether this was an issue with a small scale tweak of the model, or a problem with the model, or a problem implementing the model, because these come from simulating, and they're still working on doing better simulations. So with that, we're left with some inescapable evidence. The universe is expanding now. It was tiny, hot, and dense in the past. We see the light coming from there, dominated by light elements matching what can fuse in a short time scale as everything expands apart. Sounds like a Big Bang theory. And there's a bunch of other things related to flatness of space, amount of material that we see, development of structure, and so on, that looks like the lambda CDM flavor. But wait a second. Just how tiny are we talking about here? There is one big problem with any true Big Bang model, and that has to do with the physics of the extremely tiny. So when we think of particles, it's sort of a classical view of particles. A particle would be a ball. A ball is an electron or a proton. A ball has a certain mass, possibly a charge if it has got a charge, and a certain size. Maybe it's a point. It might be a purely zero-size point that actually carries a mass and a charge. And it's got a certain motion. You can say it's here. And it's moving in that direction at that speed. And therefore, I can predict what it's going to do, like in a game of billiards. With the very small scale, however, there is the quantum picture. And that's where things actually sort of being here is the particle, it's moving in this direction. It's actually a case of the laws of physics there are predicting how you develop the amplitudes of probabilities of measuring things. So apart from location, also things about its motion and so on have various probabilities for measurement. I'm trying to show this in a cartoon way. I think you'd sort of smear out. This would be a more yellow, like where you're more likely to find it, less yellow where you're less likely to find it. But keep in mind, if you measure it, you won't find a piece of it. You would find either entirely here, more likely you'd find it entirely here, but you could also find it entirely here, there, and so on. And why does that matter? Well, it matters when you're trying to figure out what's happening with forces and gravity, whether it's well defined or not. So a classical view of particles, you can have two particles that are separate, or they could be touching. You could have points that are any distance apart. You've got a definite distance. You can define your gravitational force. And even though general relativity goes beyond what we call classical physics, it still works for this kind of well-defined distances between masses. General relativity can't really apply if you've got smeared out probabilities, which you may or may not actually measure where these particles are. And if you do, you could have, well, they could be this far apart, or maybe find this one here and that one over there, or that one over here and that one over there. You got a whole bunch of different possibilities for the distances and therefore gravitational attraction. This doesn't cause a problem with any other force in nature. We've got a couple of forces that are just for subatomic particles that just deal with nuclear forces. And electromagnetism actually has got a way of being melded into this quantum view over here, but gravity doesn't yet. And so gravity wouldn't work in the quantum world in any way we understand yet. And that's an issue when the size of the universe gets down to a size that is smaller than you would expect for a well-defined, even a single particle. How do you even communicate across one particle, let alone between particles? And that over there is they call the Planck size. They scale things related to the quantum scale, gravity, speed of light, and so on. There's a characteristic size there, which is of 10 to the negative 35 meters. That you would expect the universe to be 10 to the negative 43 seconds after the Big Bang. But in that 10 to the negative 43 seconds, we truly don't know, does it actually clock back like lambda CDM to a true point of zero? Or does it do something else? And that, since we are talking about origins, is what I want to give you a little bit of an idea of what the heck's going on with that sort of question. So over here, problem solutions of the road ahead. Well, I've picked from that this figure here talking about various ways people are, looking at modifying gravity. I didn't think I was, now it's going crazy. Can I get this to go forward? Okay, very much, okay, here, come on. So you saw that there's all of these things here. They're modifying gravity, and I should be honest, about 95% of this, if I've got to Google, I have an idea what's going on. I am not developing gravitational theories. I'm not in the area of theoretical cosmology here, and therefore, this is kind of where you pop the popcorn and watch the catfights in the literature as to who thinks their theory is best. Or you just wait for someone to say, hey, we've got something testable, and they say, great, where's the data? One way or another, they've got entire families of different ways of dealing with it, which means basically there isn't any solid data that can help us narrow this down yet. This I recognize as being one of the ways they try to meld quantum gravity together with general relativity. But I don't know about any of these other subsets. This over here, MOND, stands for Modified Newtonian Dynamics, which means you go back to Newton's theory, toss out general relativity, modify Newton's theory to both cover all of the observations that made us discredit Newton's theory in favor of general relativity, and extend it to try to fit other things in cosmology. Basically, it's one big interesting party for the people who are interested in developing theories. Now, what this means is a few scenarios that are talked about a bit more to give you a flavor of what the various things can be. Again, there is no evidence one way or another at this point. But back all the way to the 80s, Stephen Hawking had proposed a model where he said that the universe had no beginning. This is the quantum mechanical wave function of the universe. This is the scenario we've been talking about. Everything cranks back to the Big Bang point. They would have had crank back time, and eventually time peters out into pure space. So you'd have space that's kind of smoothly ending here, but there's no time. There's nothing happening in terms of development during that. That would be called the no boundary scenario. There are others where they keep a Big Bang, but say we might not have just one Big Bang. This over is they call a modified cyclic universe, where you would have started at true time zero, but the universe wouldn't have had quite the right parameters for us. It would have expanded, recrunched it, and rebounded, changing parameters each time for some reason. And the fact that we are in this universe that is just barely expanding enough to keep on expanding forever be explained by being the first part of the cycle that could break this. So there would be a time zero that go beyond this, what we think time zero is, and we'll go back further in the past. And there are ones where instead of there being a true point at time zero, in this case, the universe remains the same tiny size for an infinite period of time, going to negative infinity there, but not developing. It's not doing anything. It's not getting any bigger. So you would have had an infinite amount of time as this teeny tiny quantum scale universe, and then at some point you can call t equals 0, it expands like in a Big Bang theory. So what does this mean? Well, in the beginning, you'd have to still have things expanding from a near point. We still see things cranking back at least down to when we start talking about these quantum scales here. From my point of view, whether time really goes to zero with a singularity, fades away, or goes to negative infinity but doesn't do anything, those are all different flavors to me of talking about there being a beginning. If there's nothing observably different about these, either from what we'll get in the past or what will happen in the future, I'm not sure we'll ever be able to address this scientifically, and it doesn't bother me because functionally it would be the same to me. There would be a point in time where things started acting like the model we have now. And as the joke goes, at some point, God said, all of Maxwell's equations, the laws of physics except electromagnetism, and then there was light. And that's my presentation.
Testing, testing. Thank you, Sarah. Thank you so much. Could you say something about the search for exoplanets?
The search for exoplanets. Oh, that's fascinating. And as you know, there are many that have been discovered. And that was actually, the Nobel Prize in Physics was split this year between Peebles got it for Explain the Universe So Outlandish CDM, and Mayer and Cuellas got it for being the first ones who, I think the way they phrased it was, found a planet around a normal kind of star. There's a deep history of people finding evidence of planets and retracting it. The first planets discovered around a pulsar, but now there's all sorts of evidence based on everything from the Kepler satellite to ground-based observations. They've been finding many different size scales of planets. There are some which are Earth-sized, some which are near what might be a habitable zone for theirs. It's a lot easier to find ones that aren't like the Earth, though, that are really close to their star or a lot more massive. That's probably what's biasing a lot of what we've been finding to this point.
Please.
Is this on?
Yes.
Okay. Yeah, thanks for your presentation. That's really difficult to cover that much technical material in a way that, ordinary people can understand. So thank you. I'm curious about the model you mentioned, the cyclic model.
See if I can actually make this work. See if I can go back 2 slides to that. Yeah, this one over here.
Yeah, because what came up at one point, remember they were arguing about, I think it's called the perfect cosmological principle, about whether the laws of physics are the same, not only through space, but through time.
Right. Laws and conditions to allow that, yes.
Yeah. Well, yeah, right. But in these models, do the laws of physics change each of those?
Yeah, again, as I said, I'm not one of the theorists who's got like the math for this, but as I understand, the reason they say it would keep on getting to bigger and bigger volume would be that every big crunch to Big Bang cycle would have a chance at slightly resetting some of the fundamental constants or the amount of material energy, density kinds of splits of things.
The fundamental constants? You mean
Possibly fundamental constants of the universe. So things like speed of light or the quantum scale could be different, or things like the amount of dark matter versus regular matter, if there's dark energy, things like that could be reset. And that's why they're basically looking for a reason why our universe looks like we're just barely able to keep on expanding forever.
So would it have been possible for life to exist during any of those?
I don't know enough about the theories to know if they would have expected some of these to actually have lasted billions of years before they get to us. And that would be kind of the time scale you'd expect for life as we know it, which took billions of years to come to be.
Yeah, because the reason I bring this up is because some people talk about the anthropologic principle. That the constants in the universe now are such that they seem almost prearranged so that we could live. But during those other...
They might not have been. This is one way of getting at what he's talking about. I forget the formulation for the strong versus weak anthropic principles. But yes, things look really good for life as we know it in the universe. But why would that be? If you could pick all of the parameters, it's very hard to do that. And so yeah, you could have had ones where it just would not have worked, and we're the first one where it could work.
But does anybody think that it would have worked?
That I don't know, because I don't know as I said, I barely scratched the surface of the literature there. The arguments don't get this nice and easy to follow, but they get to be your pages and pages of math that I don't want. I'll spend my time reading math that's more on some areas that I can study a little more directly.
It is something interesting.
It is a very interesting concept.
You would have had life for billions of years and then repeatedly.
Yep.
Okay, enough.
Thanks. The microphone there can.
So what are the basic elemental characteristics of energy and matter that allow physicists and so forth to make the predictions that they are making?
Okay, well, so in terms of energy and matter, so there's matter is, well, it has the properties that you get from gravity, which you have to put into the general relativity formulation. So it attracts itself with gravity. Energy is related to light, which also has got effects in the gravity of general relativity. But it also, as the universe expands, becomes less energetic through the redshift. Whereas when you take regular matter and you expand it, you don't make it less energetic, you just spread it further out. So that's sort of regular matter, regular energy. There's ways of predicting, if you make it expand, what's it going to do? Regular matter is just going to try to actually slow down expansion. And actually light will try to do that a bit too, from this sort of an attraction, including the energy of light. And you have to sort of put it together with sort of an expansion rate at the time and see if there's enough for it to actually slow things to a stop or not. Is that what you're trying to get at, or is there?
So I'm a molecular biologist, so I understand DNA, RNA, proteins. I know what they're made of. I know how they interact, so I can make predictions about biology.
Right.
What are the equivalent components of energy and matter that physicists actually work with? What do they write down? What do they use?
What do we write down? Okay, so there is an equation of state that gets used. So in the Friedman, Lemaitre, Robertson, Walker equations that are how you implement general relativity on a universe-wide scale, they say, all right, you have how is this going to develop going further? You take each element which has been averaged out through the universe and say, this thing is going to, as things expand, it will do this in terms of its pressure versus density. That's it. Oh, so sorry. Bosons, quarks, regular matter actually is one subset. Then there is photons, light acts differently, and dark matter, which has it acts in a different way. Dark energy acts in a different way as well. So regular matter is one component. Radiation has to be treated separately because as you expand the universe, you actually drop its energy in a way that you don't with an atom. And then the dark energy, you don't drop its energy, you just simply have more of it if space expands and less of it if space were to contract. So those are the building blocks. You don't even talk about individual atoms. So here's the regular matter. And then here's the amount of radiation density. And here's the amount of dark energy density. Is that a little more what you were trying to get at?
Yes, Bob. Oh.
Someone help him with there's a question back there.
Okay, in trying to make a connection between what you've told us tonight and what Professor Charles Boberts told us last week, his thesis was that creation involves starting with chaos and going to order. Mm-hmm. Well, it appeared that we didn't get to life, but at least we got to atoms. So we did start. Is it reasonable to say that what we were starting with before anything was put together that we were starting with what amounts to chaos.
You might be able to interpret something like this picture
Yes.
that way.
Yes.
Where you've got, all right, it's this tiny thing and it's doing nothing. Is that what is meant
That's-
by chaos? And only when, and God said there will be, let there be light and so on, this expands outwards, you allow things to develop is going towards order.
So the attractive forces then were finally able to overcome the energy, the excess amount of energy that was present at the beginning, and start to form atoms, which could then form molecules, which can then go to the amino acids and the organic molecules, and it allowed for life.
Yes, as you expand, you will get to that point where atoms as we know it exist, and then that allows, well, life as we know it needing things heavier than lithium. First, you better make some stars to burn things to heavier elements, and then you get to try to make, molecules like we know them, and then life as we know it, yes.
But there is a connection.
You can make that connection. I'm not saying that all scientists would make that connection.
I know that, but
I think it's a perfectly reasonable connection to make.
that would seem to be based on the title of this series, what it is that we are trying to do.
There was someone over there, I'm not sure who it was.
Well, I had a different question earlier, but that conversation just made me trigger. So one of the nuclear physicists, and he teaches Old Testament, his basic creation story says there was God, there was wisdom, the laws of physics before something to act on. There's the Big Bang, energy, matter, life, mind.
Okay.
Does science ever think it's in the world of taking all of this and ultimately saying, then how do we get to mind?
That area, I think, is neuroscientists work on, and some of this is a subset of that now, in terms of what is conscious. I've heard of people studying things like you seem to make decisions before you realize that we've made them and stuff like that, but I don't know much about that area.
Sarah, thank you for a wonderful presentation. As one of our respondents said, I knew this was going to be a super challenge. There's so much information, but thank you for presenting it to us in a way that I think we could at least see where the general direction goes and the ideas. Thank you so much.